Hello, this is Midterm 2 on Module 6 and 8. So, to get right into the first question, what we're going to be doing is we're going to be converting these hexadecimal codes into binary, and then we're going to be looking for the 6-bit opcode in order to be able to understand what instruction we're really looking at. So, to convert this hexadecimal code into binary, it's going to be 0011, 0000, 1000, 1010, 0010, 0000, 0000, and then 0010. And then we're going to be using the testing reference sheet in order to be able to understand what instruction the 6-bit opcode corresponds to, which is going to be now 001100 corresponds to 0x0c in hexadecimal, which corresponds to and immediate, like the instruction. So that means it's going to be an I format instruction, which means that there's going to be 5 bits for RS and RT, as well as 16 bits for the constant. So 00100 is actually 4 in decimal, which if you look at the register encoding here, it's actually going to be register A0, and then 01010 is going to be 10 in decimal, which corresponds to register T2 if you look at the register encoding yet again. And then these 16 bits are just 2 in decimal. And so really the whole command is just going to be and immediate T2A02. And now for the second part of the question, we're going to be converting this hexadecimal code to binary, which is going to be 0001, 0001, 0100, 0000, 0000, 0000, 0000, and then 0110. And now we're going to be using the testing reference sheet in order to be able to see which instruction does the opcode correspond to. And we look at this opcode, it's going to be 0x04 in hexadecimal, which corresponds to branch equivalent, right? Which means that it's going to be dissected in a similar format to the previous question. It's an I format instruction, which means that there's going to be 5 bits here, 5 bits here, 16 bits. So these 5 bits are going to be 10, which corresponds to register T2 like we've seen before. And then 0000 is just going to be the 0 register. And then these 16 bits are just represent 6 in decimal. So really what this command, or this instruction rather, is going to be branch equivalent to T2, 0, and then 6. And now for the second part of the question. So to calculate the energy needed to complete execution of the program listed above, we're going to find out how many instructions we have of each type, and then we're going to multiply them by their corresponding energy cost in order to be able to get the total energy cost required to execute the program. And so it's going to give us 70 microjoules in total. And then to compute MIPS per milliwatt, we're going to have to first find MIPS, which means that we need to first find the number of clocks required. Now, since we have 1 set, 2 read, 1 write, and 5,000 add branch instructions, which come from the loop, that's going to give us 60,020 clocks, which came from multiplying each of these instruction types by their respective CPIs. And now we just multiply these total clocks by the number of picoseconds per clock in order to be able to get the total time. And to get the MIPS, we're going to get the number of instructions, and then we're going to convert those instructions to millions of instructions and then divide them by the execution time to get a 750.7 millions of instructions per second. And then to find the power in milliwatts, we're just going to be dividing the energy cost in total divided by the total execution time to get us 3,520 milliwatts. And then to find the MIPS per milliwatt, finally, it's going to be 750.7 MIPS divided by 3,520 milliwatts, which is going to get us 0.213267 MIPS per milliwatt. Thank you very much.